So the title of this is stoichiometry, and of course what you guys just handed in was balancing equations using stoichiometric coefficients. So stoichiometric calculations must use those stoichiometric coefficients. So now we can talk about this. So stoichiometric or calculations are important in chemistry, and basically they're relating amounts of two things, 2 to 3, 4 things. They could be amounts of reactants or amounts of products. So, like I said, when you balance the equation, what you handed in, you actually came up with the relative amounts of reactants and products that would be formed, okay? So the stoichiometry is given by the balanced chemical equation. My go-to is this decomposition of water, which can be done with electricity. Oops. So this is the lab that you did earlier this semester where you burned magnesium. Basically, you heated it up and it combined with oxygen from the room to form a new substance, magnesium oxide. Now, if I was to balance this, I would, and you would too, put a 2 in front of the Mg, leave a 1 in front of the O2, put a 2 in front of the MgO. You have the same number of atoms of each type of element on both sides of the reaction arrow. I generally think of it as this, that we have 2 atoms of magnesium, 1 molecule of O2, and 2 formula units of magnesium oxide are formed. Alternatively, we can look at those coefficients of 2, 1, and 2 across the board as not on a small scale, but kind of scale them up. We could say, like this says in red, that 2 moles of magnesium will react with 1 mole of O2 molecules to form 2 moles of magnesium oxide formula units. So this actually, at the end of the lecture on Wednesday, when I had a fractional stoichiometric coefficient, we have to think of it in terms of that. And we're actually going to, it's the concept of the stoichiometric coefficients as relating relative moles that we're actually going to run with when we talk about stoichiometric problems. Okay. So these calculations then deal with the stoichiometry of the equation. You can't do these sort of problems unless you've balanced your equation first. And all it is to get to amount of something. Given the amount of something, you get to the amount of something else. Okay. So I kind of likened it to, I looked this up on the internet, one recipe for brownies, and I think I'm missing vanilla and baking soda, maybe, over here on the reactant side. But the little squiggly marks actually could be our stoichiometric coefficients. So with a stoichiometric ratio, we actually pull those coefficients and make a ratio out of it. What a ratio is where you basically have a numerator and denominator. We've used ratios earlier in the course to convert from one set of units to another set of units. So your stoichiometric ratio is going to come from a pair of your stoichiometric coefficients from the balanced equation. So for instance, if we go back to this one, where our magnesium is reacting with oxygen to form magnesium oxide, the relative number of moles present are 2 moles, 1 mole, and 2 moles. We could come up with actually a set of 6 stoichiometric ratios. The first pair of stoichiometric ratios is simply relating the moles of magnesium to the moles of O2 molecules. So notice that from left to right, these have the relationship of the one on the right is the inverse of the one on the left. It's just flipped. We could, instead of both focusing on the reactants, we could focus on one of the reactant and the product, magnesium and magnesium oxide. This is where sometimes students say, Mrs. Snipes, you're being silly. 2 over 2 is the same as 1 over 1. I will argue that 2 moles of magnesium over 2 moles of magnesium oxide gives you more information than if I would reduce it right away. But you're right. Again, what do these have in common, the left to right? They are the inverse of each other. The last possibility would be to focus on the moles of O2 relative to the moles of magnesium oxide. The relationship is 1 mole of O2 will be required to form 2 moles of magnesium oxide. Again, these are all coming from the stoichiometric coefficients from the balanced equation. So if I call this one A, we're going to work some problems here, B, C, D, E, and F. And if you want to, you can jot those down because I'll be referring to those. We're going to use those ratios to work some problems. The first problem actually is well, that's a baby problem, sort of. You're going to see that the other type of more common stoichiometry problem doesn't deal with moles like this, it deals with grams. But we're going to work 2 problems. What I like to do sometimes is to take the information from the problem and to kind of put it underneath the species it's talking about. So it says how many moles of oxygen, and remember the thing in brackets probably won't be there. So how many moles of oxygen are needed to react with 0.245 moles of magnesium? So I'd find my O2 and I would write question mark moles underneath there. And then I would find my Mg and I would write 2.45 moles underneath there. So that's the problem. That is the first problem. The second problem is this. How many moles of magnesium oxide now, so question mark moles of magnesium oxide can be produced, and actually it's understood, it's poorly written on this slide, understood that we have 0.245 moles of magnesium and sufficient oxygen. So I'm going to go ahead and put, goodness, 0.245, my bad. Final answer. And that will be our second question. Okay, so again, stoichiometric calculations are simply, we have a quantity, in this case, of magnesium. We're supposed to find out the quantity of O2 in the first problem, the quantity of MgO in the second problem. And we're going to use those A through F stoichiometric ratios. Okay, so to get from moles, the first problem, to get from moles of magnesium to moles of O2, I want you to, if you jotted them down, A through F, go back and see which one has moles, which one can get us down the road. So what we've done before is I want moles of magnesium to cancel, be left with moles of O2. Just think A, B, C, D, E, or F. Jotting down. So we want moles of magnesium to cancel. So we want the bottom. Yep. Very good. So I'm going to ask a follow-up question. So this will get us down the road. 1 mole of O2 over 2 moles of magnesium. Where did those come from? They came from the stoichiometric coefficients in the balanced equation. So follow-up question, question number 2. Which ratio will we use here? You don't have to say A, B, C, D, or E. What's going to be, we want moles of magnesium to cancel. We want to be left with moles of magnesium oxide.
D.
D? Is that 2 moles of magnesium oxide over 2 moles of magnesium? Exactly. So again, this is kind of like the baby stoichiometric calculation. It's kind of what I call the heart of the stoichiometric calculation, going from moles of something to moles of something else, and all we're doing is using the stoichiometric coefficients from the balanced chemical equation to make a stoichiometric ratio. So let's knock these out. So the first one, The term in both of these cases, the first term is going to be that 0.245 moles of magnesium. I would usually put it over 1. And then we're going to slip in that stoichiometric ratio, 1 mole of O2 over 2 moles of magnesium. Now, when we've been balancing our equations with stoichiometric coefficients, in this case a coefficient of 1, a coefficient of 2, those are exact numbers. They introduce no uncertainty to the problem. So you're looking at 3 sig figs. So simply then the amount of O2 that must react with that amount of Mg is 0.123 moles. So let's knock out the second one. So again, the starting number is going to be that 0.245 moles of magnesium. I put it over 1. And if we let the units do our heavy lifting, we decided we want moles of magnesium to cancel. We want to be left with moles of MgO, magnesium oxide. So this is where we have our 2 moles of magnesium oxide over 2 moles of magnesium. If you want to, and sometimes I'll have students that don't want to put the 2, they want to put the 1 to 1. And I think that's fine. I think it could really confuse you down the road, but that's fine. So moles of magnesium will cancel. We're left with moles of magnesium oxide. Again, 3 significant figures. I can do the math there. So no calculator required. 0.245 moles of magnesium oxide. So the reason I actually did this little recipe thing up here is I feel like when you balance the equations, like you guys did, some homework and handed it in, you're coming up with relative amounts of the reactants that you need in order to get a relative amount of product. So for instance then, we could come up with stoichiometric ratios. Let's say I go to my cupboard and let's say I've got 4 cups. I have 4 cups of butter. And let's just say I've got tons of everything else. So we're going to talk about limited, the reactant. In the case of a recipe, the reactant are your ingredients. We're going to talk more about which reactant is in limited supply later. But let's just assume that I've got 4 cups and gobs of those everything else. And I want to know how many brownies I can make. So the deal is, you might say, well, I can get 4 sets out of, I get 8, right? I can get 8 sets out of my 4 cups, and so I can scale my brownies up to 8 times 16. And you're right. But this procedure actually, and you need to work problems using this for a reason, just take my word for it. Kind of following this similarly, we would say, I have 4 cups of butter, and I'm going to come up with a stoichiometric ratio where I want cups of butter to cancel, and I want to be left with brownies. And when you're working these problems, if you just focus on the units first and then go up to grab your stoichiometric coefficients, it works better. So our 1/2 cup of butter is going to go down here. I'll put 0.5, how's that? Is that 1/2? And then our 16 brownies is going to go right there. Now I know that looks weird. You're like, really? But if I take 4 times 16 divided by 0.5, then that's the right answer.
So
it's the same thing as taking 8 times.
Moles of MgO produced. Why is it 2 moles of MgO?
That's to balance it. That's to get the same number of atoms of magnesium and oxygen on both sides of the reaction arrow. And just subtract. Oh, wow. So now this is going to bug me. Can't believe I can't find my calculator. Let's put it in my office. Okay, do it this way. Serious. All right, dang, that's a lot of brownies. So I get 128. And I'm not sure how I want to round it, but I'll just go ahead and leave it that way. Okay? So, again, that's kind of the heart of the stoichiometric calculation. We're going to kind of scale that up. So these problems will be due when we meet again on Friday, or Monday. Now this actually is hopefully hitting you over the head a little bit more than maybe my exam that I gave you for your Unit 3 exam. You have to show all of your calculations. So for instance, if you have to calculate a molar mass, show that. Show however you work the problem, and notice that you have to work the problem the way I do. And you'd be like, oh, are you serious, Mrs. Snipes? I'm like, yes. So there is a reason for that. All right. All right, so let's take it up a notch, and you'll see how this one's a little bit different. So I'm going to write underneath the thing what I'm after, or what I know about that thing. So what mass is needed of oxygen? So I find my oxygen, I'll write $G for grams. And notice that we have, now we have the mass of magnesium. So 0.30 grams of magnesium. So that's my problem there. I'm going from 0.30 grams of magnesium to grams of O2. The catch here is, and it's on the next slide, when we came up with that ratio, what was it? We used 1 mole of O2 over 2 moles of magnesium. Notice 1 mole of O2 over 2 moles of magnesium. These stoichiometric coefficients relate to moles, not to grams. So I cannot use a quick and dirty stoichiometric ratio like I did before to get from grams of magnesium to grams of O2. You're going to see a very common pattern now. We know we can get from grams to moles using the molar mass. So if I were to rewrite this, I keep going back and forth. I can go from grams of magnesium to moles of magnesium using its molar mass. MM stands for molar mass of magnesium. Then I can go from moles of magnesium to moles of O2 using the stoichiometric ratio that we talked about just a minute ago. And then finally, I can go from moles of magnesium to I can go from moles of O2 to grams of O2 using the molar mass of O2. So what's different about this problem is these kind of front-end problems. So we can use the molar mass of magnesium. I love that phrase, to go from grams of magnesium to moles of magnesium. This is just kind of showing you a flow chart of how we can work this problem. We can use a stoichiometric ratio, just like we did in the previous problems. When you're going from moles to moles, then you just use your stoichiometric ratio from the stoichiometric coefficients, the balanced equation, and then we'll have moles of O2. And then to go to moles of O2 to grams of O2, we need to use the molar mass of O2. I mentioned showing all of your work. So, for instance, you would need to show this work right here, calculating the molar mass of O2, taking 2 times how much 1 oxygen weighs, because we talked about this sort of calculation in Unit 3. All right. So I'm going to knock out all of the molar masses, if that's okay. The molar mass of magnesium is simply the decimal number for magnesium. 24.31 grams per mole are the units for molar mass. So we're going to get some more practice at using molar mass as a conversion factor. The molar mass of oxygen, I need to take 2 molecular oxygen. I need to take 2 times how much 1 oxygen weighs, which is 16.00. And then again, units of molar mass are 32.00 grams per mole. And I'm going to go ahead for a follow-up problem here in a minute. We're going to actually come up with a mass of product form, the mass of magnesium oxide. So we'll go ahead and knock out its molar mass. So I need to take 1 times 24.31 plus 1 times 16.00. and you're looking at 40.31 grams per mole, its molar mass. All right. Remember though, one of the things I tried to emphasize in Unit 3 was this whole G/MOL. What that really means is this. I'll pick on magnesium oxide. For magnesium oxide, that means there are 40.31 grams, and I'll go ahead and put MgO. I'll be what we say more explicit, because actually per 1 mole of MgO, you're going to need that sort of extra information when working these problems. But I just kind of unpacked that one, for example. All right. My favorite way is to string up all of the terms, kind of the strategy I showed you a minute ago with the arrows. I like to string them all up in one calculation. Every once in a while I'll have students that like to kind of break it up. So either way. So here we go. My first term is going to be the mass of magnesium over 1 that was given. My strategy is to take the mass or the grams of magnesium and get to moles of magnesium. I'm going to use that 24.31 grams per mole, but I want grams to cancel and I want to be left with moles. So we're using what I call the flipped version of the molar mass. 1 mole of magnesium over 24.31 grams of magnesium. Every once in a while I'll have students that tend to not want to, well, probably because I didn't in previous problems, be explicit. You have to say what species, in this case, what reactant you're dealing with. So now we're then to the grams of magnesium cancel, and we're left with moles of magnesium. We're kind of to the heart of the stoichiometric calculation. Now we're just going to use that ratio that we used before, where from the balanced chemical equation, I know that 2 moles of magnesium will react for every 1 mole of O2. So this is our stoichiometric ratio. Moles of magnesium cancel the way I used my stoichiometric ratio. I'm left with moles of O2, which I'm almost done then because I want grams of O2. To finish up the problem, I need to use that 32.00 grams per mole for O2. And in this case, I'll use the unflipped version. So this is the molar mass of O2. 32.00 grams of O2 per 1 mole of O2. Moles of O2 cancel, and we're left with units of grams of O2. Kind of the theme of working numeric problems in physical science is to make sure that your units have canceled, you're left with the correct units, which is perfect. Rounding wise, it's looking like I have 2 sig figs in 0.30. I have 4 in the molar mass of magnesium. There's no uncertainty brought by the 1 or the 2 here. I have 4 sig figs here in the molar mass of O2. So I need to round to 2 sig figs. So you're looking at 0.20 grams of O2. That's your answer. So it really takes on this pattern of we are given the grams of something, we use its molar mass to get to moles. The next step is going to be that stoichiometric ratio to get to the moles of something else, and then we kind of have to unpack those moles to get to grams. So use the molar mass of that last thing. It's a very nice cadence to it. So we're going to do one more follow-up problem. And in this case, we are going to, it looks like this. What mass of magnesium oxide is produced? So question mark grams of magnesium oxide when we have 0.30 grams of magnesium, 0.30 grams. And we'll be talking more about this. This is kind of like what I said when you're going to make brownies and we have so much butter and lots of everything else. The lots of everything else, we're going to actually use the word sufficient oxygen. So that means you're not going to run out of it. Which actually, a minute ago, sufficient oxygen, we said actually it's got to be greater than what? 0.20 grams. Okay, so to work this problem then, it's going to be like this. We're going to go from mass of magnesium to moles of magnesium using its molar mass. And then we're going to go from moles of magnesium to moles of magnesium oxide using a stoichiometric ratio. Stoich ratio.
And then we're going to go from moles of magnesium, oxide, moles of MgO to mass of MgO using its molar mass. And that's why you saw me knock out the molar mass a minute ago. Okay.
I have a question.
Uh-huh.
So in the book or like in future problems when it says sufficient, are we gonna have to calculate what sufficient is?
No. And that'll be, I'll come back to the sufficient when we identify the limited reactant.
Okay.
So that kind of thing. So it will be given to you. Okay, so our first term is going to be that 0.30 grams of magnesium over 1. Like, this is going to start out just like the previous problem, where now we're going to use the molar mass of magnesium, the flipped version, because I want grams of magnesium to cancel, be left with moles of magnesium in the numerator. So this is where if you did break it up into parts, you'd already have the moles of magnesium ready to go. But now we're ready for the stoichiometric ratio, and we want to get from moles of magnesium to moles of magnesium oxide, because that's where we want the mass of that, and before we get the mass, we need the moles. And this is where I said I would go ahead and leave my 2 and 2 because I can clearly identify the number 2 in the balanced equations. The number's 2 in the balanced equation. All right, so once we have moles of magnesium oxide, we just need its molar mass to finish the problem. A few slides ago, said it was 40.31 grams per mole. So again, we have to use this unpacked version of the molar mass, and it's the unflipped version of the molar mass. And in this pattern, in this cadence, that will always be the case. We use the flipped version first, molar mass, and the non-flipped version last, molar mass. But if you let your units cancel like they should, that'll be homologous. So unit-wise, your grams of magnesium oxide, which is perfect. We again need to round to 2 significant figures as limited by the mass of the magnesium. So you're looking at 0.50 grams of magnesium oxide. This is where oftentimes students will say, well, Mrs. Snipes, if this was 0.30 grams, and you know it's going to react with 0.20 grams, then it should be a no-brainer that that will be 0.50 grams. And you're right, that's actually using the law of conservation of matter. So on a test, just to kind of put you at ease, I will never put you in the awkward situation of having to work this out longhand when you could have gotten it short like that. I will say this is a good check, okay? So here in a minute, we're going to be doing some, I'm going to turn you loose with a few calculations, and you should always have this mass balance going on, okay? It's a good, like I said, a good check. Okay, now, I think I moved these. Do you guys have something with like 2 products, 2 reactants in the next slide? Or do you have this one? Okay, so go a few slides from now. Yep, on the next page, yep, page 5. So I'd like to do this one instead, and then I'm going to kind of turn you loose we're going to come back to this one before we leave. All right. So sometimes it's like, oh my gosh, you do 10 billion of them, but that's how we get good at it. So let's see, this is balanced. We have 1 mole of P4 reacts with 6 moles of Cl2 to form 4 moles of PCl3. Where I had those red lines, those are going to be the heart of our stoichiometric calculation. Okay, so those are relative moles, so keep that in mind. We have a couple of problems here. The first problem looks like this. So what mass of P4, so question mark grams under the P4, is needed to react with 1.25 grams of Cl2? The second problem looks like this. Come back. The second problem says what mass of PCl3 can be formed. So underneath my PCl3, I'm going to put 1.25 grams. And be formed from 1.25 grams of Cl2. I'll put that under my Cl2. And notice that it's sufficient. Again, and what does sufficient mean in this case? We're actually going to answer that question after we answer 1. Oops, sorry. Drat. This should be question mark grams. I'm sorry. Final answer, question mark grams. Spacing off there. Okay, so let's work those couple of problems together. So I need to knock out some molar masses. Molar mass of P4 is 4 times the decimal number. You guys have all these. 4 times the decimal number of 1 phosphorus. The molar mass of Cl2 is 2 times the decimal number of 1 chlorine. And the molar mass of the product is 1 times the decimal number for phosphorus plus 3 times the decimal number for chlorine. Now, one of the things I have seen over the years, students get confused, and I'm not quite sure why. But notice when we came up with these molar masses, we did not use the stoichiometric coefficients. We just knocked out molar masses. We didn't use the 6 for the Cl2. We didn't use the 4 for the PCl3. I have seen every once in a while a student that uses some funky sort of pattern for their stoichiometric calculations, and they use them. I wouldn't suggest it. All right, so let's knock out the first question. So the first question was given the mass of Cl2, so that's going to be our first term, 1.25 grams of Cl2 over 1. Again, we have to be explicit. We have to say Cl2. Let's go around the room. So, Gabe, what will the second term be?
1 mole of Cl2 over 70.9 grams?
Yep, of Cl2, yes. 1 mole of Cl2 over 70.90 grams of Cl2, perfect. Okay, so what do you think, RJ? Now I'm ready to go from moles of Cl2 to moles of P4. Stoichiometric ratio, what does that look like?
So you're going to put P4?
I'm going, I want to try to get to moles of P4.
Okay, so you're going to need 1 mole of P4 over 1 mole of Cl2.
Almost. 1 mole of P4 over how many moles of Cl2?
6.
Yep, perfect. 1 mole of P4 over 6 moles of Cl2. Awesome. So over to you, Cole. So on the previous slide, you had the molar mass of P4. We need to use that now to finish up the problem. We're going to use the molar mass of P4 we have on the previous slide. We want moles of P4 to cancel. We want to be left with grams of P4.
So we 1 mole P4 over 123.88 grams per mole.
Well, if we did that, then if we put mole P4 up here, that won't work. So I need to put mole P4 down here.
Yeah. 123.88 grams over
Yeah, 123.88 grams of P4 over 1 mole of P4. Perfect. So, Gabe, how many sig figs do I round it to?
30.
3. Nice. So, in your calculator, if you take 125 times 120, if you take 1.25 times 123.88 and you divide that by, in the denominator you have the quantity 70.90 times 6. You should get this number. Okay? Let's do the next one. And we'll go backwards. Okay, so a follow-up question was the same mass as Cl2, and now what mass of product can we produce? And again, yeah, I know you could just add the 1.25 grams of Cl2 to the mass of P4 and come up with this, but we're going to do it the long way. Okay, so Cole, help me out. How can I get from grams of Cl2 to moles of Cl2? A few slides ago, I had the molar mass of Cl2. .90. So we want grams of Cl2 to cancel. We want to be left with moles of Cl2. And the previous slide says the molar mass of Cl2 is 70.90 grams of Cl2 per 1 mole of Cl2. So how could I use this? There.
Flip it.
Flip it. Flip it good. Yep. You got it. So if I flip the molar mass, and again, that's always going to be kind of the cadence to this sort of problem. Grams of Cl2 cancel. We're left with moles of Cl2 now. I'm going to skip you, RJ. I'm going to go over to Gabe. I'm going to come back to you, RJ. So Gabe, how can I get from moles of Cl2 to moles of PCl3?
If I 4 moles of PCl3 over 6 moles of Cl2.
Yep. I get excited when I get these big numbers, but these stoichiometric coefficients. For my ratio here, my stoichiometric ratio, I'm going to use the stoichiometric coefficients, and I want moles of Cl2 to cancel, and the coefficient in front of it is 6, so 6 moles of Cl2 is going to go in the bottom, and I want to go to moles of PCl3, and the coefficient in front of that is 4, so I'm going to, I have to bring down my 4. That's the ratio, that's the recipe. Cool. So moles of Cl2 cancel. And then RJ, how can I go from moles of PCl3 to grams of PCl3?
You're going to multiply it by 137.32 grams of PCl3 over 1 mole of PCl3.
Perfect. Yep. Use the unflipped version of the molar mass of the PCl3. Very good. Now moles of PCl3 cancel for units of grams of PCl3, so I'm in good shape. So Cole, how many sig figs are we going to round it to?
3.
3. I'm liking it. So you're looking at 1.61 grams of product.
Now, do you put that in the calculator again?
So in the calculator, and you guys are gonna get your own work at this here in a minute. I'm going to pick all the numbers that aren't 1 in the numerator. So 1.25, I'll just put parentheses around the things to show that they're multiplied. Also in the numerator, I have 4. Also in the numerator, I have 137.32. And in the denominator, you're looking at 70.90 and also the number 6. So some people like to go ahead and multiply this and get a number, and then this and get a number, and then do one last division. What I like to do is I use parentheses. So I'll open parentheses, 1.25 times 4 times 137.32, close parentheses, hit my divide by key, open another parentheses, which is for the denominator, 70.90 times 6, end parentheses. So, all right. So now, dun, 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 back to this one. So stoichiometric calculations just go from the mass of something, usually the mass, not the moles, the mass of something to the mass of something else. We've got all sorts of possibilities here. But I just want you to do as many as you can do in the next 8 minutes. So they look like 2 questions, but within those 2 questions are some sub-questions. So notice that for all of these questions, my starting point is, let me find oxygen, 0.143 grams. I know it feels weird, but we're going to go from the mass of the product to find one of the 3 products to find some other masses. So for the first one, what mass of each reactant has reacted? So this could be like 1A, grams of this one, 1B, grams of this one, and then this one, the number 2, what would be the mass of the other products? So there's 4 questions here. So this would be 2A, question mark grams. This would be 2B, question mark grams. And you guys have this, right? Do you guys have the molar masses of everything? Yeah. Okay, so go ahead and take a stab and work together if you want, or I'll be walking around, but you should have an assignment slide coming up then. That assignment will also be due when we meet again on Monday. while you're working them, I will be kind of working them up here just to make sure if you guys have any questions, you can kind of double check your answer. Bless you. Bless you. Oh, is this a normal? Did you not move it? There's no. Okay, okay, good. Okay.
Yeah, so do the price first.
That's okay. But it's working for you. Very good. I'm cheating. On the first one?
I think it's good at one, but 34.26 up to 34.3.
Kind of fun.
You want a little bit overdone?
Yep. In fact, you don't have to do all of these, like put even just awards, so you can kind of make sure you're on the right track. But, and then don't forget this assignment slide, this is also due on Monday. Down road.
Okay.